So after logistic regression, we're going to start talking about, which was using stats models. We'll start using some of the classifiers from scikit-learn. So the first one we'll fit is this LDA model. So the way scikit-learn works for these prediction problems is there's some object, in this case we've called it LDA. That was just a shorthand for linear discriminant analysis. That sort of tells, we don't give any data to the classifying object here. We just give some arguments, like in this case we asked it to store the covariance in case we want to inspect the covariance matrix in LDA. But having formed the estimator this way, we later fit on a matrix of features and a response y, and then we can predict on new features or the original features. So that's the general way that these estimators all work. Okay, so we're again going to split into test and training. And so we'll make our training and test sets as follows, and we're going to fit on the training data.
So, Jonathan, we're using the same train and test design matrices we had before, but you just drop in the intercept from those. Is that right?
That's right.
Yeah.
Yes, yes.
Because LDA doesn't require you to put an intercept column.
Yes, and I think it will actually complain because the the covariance will be 0. Okay. So yes, it will have a non-invertible covariance. Okay, so as we saw in the lecture, there are a few different parameters that come from fitting the LDA model. One is the common covariance. There are within-class means that you can find this way. There's the label of which class is which. This just helps. If down is the first one, that tells us that now this is 2 by 2. We'll have the documentation, again, as scikit-learn has great documentation, will tell us whether the second row is the mean in the class or the second column is the mean of the up. If we had used 3 features, we would be able to tell here because we would have a 2 by 3 or a 3 by 2 matrix. But the documentation will sort it out. My guess is that it goes by row as the major index. But okay, so these quantities are parameters of the fitted model, and this scalings matrix here, this actually tells you the discriminant function. That's what's used to make the prediction between whether you're in the up class or the down class. Okay, so we'll want to again evaluate how well this classifier does on the test data. So we'll use now the second method that's commonly used for scikit-learn classifiers in any case. It's the predict method. Having fit on X train and Y train, we predict on X test. And we'll again form the confusion matrix using the same function. We have the same test labels. So we haven't printed out the, well, let's see if we've printed, we have not printed out the accuracy. But so let's move on. Okay, so we'll just pause here for a moment to say that most of the time we've assigned points to classes based on thresholding the probability at 50%. Though sometimes we might decide to change that, and we can easily do that by just changing the threshold we apply to these probabilities. This LDA probability vector, these are the estimated class probabilities for the prediction, the test data. So the first column is the estimated probability of being in the up class, and the second column is the estimated probability of being in the down class.
So I guess if you increase the threshold, you'll classify less observations in the up class and more in the down class.
That's right.
And that'll change those 2 off-diagonal errors that you have in the confusion matrix.
Yes, and I saw in the text that it's actually, the first column is the down class. So the effect that will be is if we increase the threshold to 90%, we'll just predict fewer in the down, and the number in this row will get smaller. But it's possible that the accuracy will improve by, well, depending on the balance of how many are up and down, and the within class accuracy. Okay, so let's move on to our next classifier. The next classifier is quadratic discriminant analysis, or QDA. And remember that this is very similar to LDA. The main difference is that there's a class-specific covariance matrix. So in terms of code, we're going to fit it, as promised, it fits almost identical to LDA. We have the same training features and the same training labels. We'll call the fit method on QDA. And this little QDA is an instance of the QDA classifier. And again, we've asked it to store the covariances. So with this, we can, for instance, look at the within the down class covariance. That would be the first covariant entry of the covariance returned.
So just to remind you, because we now allow a separate covariance matrix in each of the classes, 2 in this case, the classification function becomes a quadratic function.
That's right.
Whereas by having that convenient assumption that they were the same, if they were the same, that led to linear discriminant analysis, was a linear function.
That's right. So the discriminant function in QDA is not described just by the scalings matrix. You need both the covariance and the difference in means. The scalings in the LDA example is essentially the difference in means, well, multiplied by the inverse of the covariance matrix. Okay, so again, in order to evaluate how well this classifier is doing, we use the predict method on our test label, our test features, and then we use the same confusion matrix, or the confusion table function, to produce the confusion matrix. Okay, and so here we see the QDA is about 60% accurate. That's even better than, I think we had 55% accuracy with these features in logistic regression. So this is actually quite good for the financial data. So, okay. So hopefully you now see the pattern, having seen it twice for 2 different classifiers. For the sklearn, it's, once you know the pattern, it's quite easy to fit many different classifiers. So we have a few more to fit. One is naive Bayes, and then we'll wrap up with K nearest neighbors classifier. So recall from the lectures, or you can read in the textbook, that the naive Bayes, when you have continuous features, naive Bayes is essentially quite closely related to QDA. It's just sort of a restricted version of quadratic discriminant analysis. In terms of the code, again, it is fit identically to QDA and LDA. We call the fit method on our training features and training labels, and then we'll evaluate in a similar fashion. So I mentioned it's quite related to QDA. Essentially, it just imposes the constraint that the covariance matrices are diagonal for QDA. That's basically the difference between naive Bayes and QDA. So it's a simpler model. It has fewer parameters than QDA, but otherwise quite similar. Okay. So just like QDA and LDA, there are within class parameters that you can examine as the output of naive Bayes. For instance, the covariance matrix being diagonal means within class you only have to store the variance of each feature to describe the diagonal matrix rather than the covariance. So this variance underscore attribute has the within class covariance matrix, the variances of the lag 1 and lag 2 for class 0 and class 1, or class down and class up. Okay, and if you want to see more about what these attributes are, if you look at the help for the naive Bayes object, it will have its doc string that describes what these attributes are. And that's similar for the LDA object and the QDA object, if you're ever curious about how to find their names. Okay, so let's see how well our naive Bayes predicts. We form the confusion table in a similar fashion, and we get around 59%, very close to LDA.
They're all doing, all these discriminant analysis methods are doing reasonably well.
Yes. Yeah. Okay. So our next topic will be K nearest neighbors.